Okay, so welcome to lecture 37. Today we'll talk about the CMOS inverter. And so the first 15 minutes of lecture today was for Eta Kappa Nu course evaluations. Looks like you did that. A couple more announcements. Homework 11, you know, is online. That's due next week during the RRR week on Tuesday. Less than 2 weeks from now, I should say. This is no longer more than 2 weeks from now, so... should really just erase this whole thing, which I'm going to do. And then Lab 6, you know, is due 5 p.m. Friday, December 13th, also next week. How's that lab coming along? Okay, lots of smiles and laughter, which tells me things are going well. So, where are you on that lab right now? So, because we can't really extend that deadline, right? That won't be extended because you got your final exam the week after that. So at this point, I would say you should have a design for transistors and that. I'm trying to look at the reaction for that, whether you have the design or not. And then I would say by the end of this week, hopefully you have at least starting to build your circuit and that sort. Because you want to leave a lot of time to write the report too. So I know what's going on. I know you've got a bunch of other projects probably going on in other classes too. Maybe those are due earlier or something. Is this the case? Okay. So in the future I need to assign this to be due a little earlier then. So those are the ones that take priority. But all right. Hopefully you'll be on your way to finishing this project. It's finishable. It's doable. And so I think when you do it, you're going to have a lot of fun doing it, despite what you may think, right? When it starts working and everything, you're measuring everything that you're supposed to measure, it's going to be a lot of fun. So get started at least if you have not, okay? Let's see. So today's topics, last time we were looking at the MOS inverter with a resistive load. So we're talking about digital circuits now. Today we're going to finish that discussion, say what the problems are with that, because that's not the way inverters are made. We do something different. We actually use static CMOS inverters or other types of CMOS inverter. We'll explain why CMOS is the better way to do it. We'll talk about the output low and output high voltage and the input low and input high voltage, how we define those for the static CMOS inverter, and that takes a good amount of math. After that, not in this lecture, but the next, we'll talk about dynamic CMOS inverter behavior, because when you think of a digital circuit, what's the most important thing that you care about? It's how fast it works, right? How fast could that clock be? And the speed of that clock is really dependent on how fast a signal can propagate through your inverter or NAND gate or NOR gate, which we're looking at now at the transistor level. If we can get to it, we'll talk about ring oscillators. And definitely we'll talk about inverter propagation delay before all is said and done. But this is kind of lecture topics over the next few days. This is our last week of lecture. And so by Friday, hopefully we'll cover most of these things. I'm learning a couple things that have changed about our curriculum that are interesting. So 151 actually doesn't go into a lot of transistor detail anymore like it used to. To get that transistor detail, you take 241B. Which is a graduate class and an advanced graduate class. So that's different because we used to have that at the undergraduate level. So it looks like your undergraduate education is going to come in this week in terms of understanding how a CMOS inverter works at the transistor level. Okay, and I think we can do it. I think we can get most of the important things for you just this week. Okay, so last time started digital circuits. Let's just review a little bit since it's been a whole week since you've seen this. And I'm seeing that you're watching the videos at least online. I can count the number of times people are viewing the videos, so I think most people are viewing the videos if they're not coming to lecture. But we went through this. This was the analog stuff. Then we started talking about digital. And we talked about, finally, what this digital is. So digital really is ones and zeros, right? And so when we're looking at it in terms of actual implementation, a 1 is a high voltage, so that's VDD. Okay, a 0 is a low voltage, it's probably ground. Okay, and so we're using transistors to switch the output and inputs from VDD or ground, or as close as we can get to them. And so that's how we represent ones and zeros. It's just by a high voltage or a low voltage. And so we went through taking a look at things at sort of the gate level. So these are inverters. We talked about the importance of noise margins. And we talked about this in particular, that the voltage transfer characteristic for an inverter ideally would look like this, but in reality it looks like this. Okay, so we have a gradual transition from high to low. And that slope of that gradual transition, you now understand where that's coming from, because you've measured things like this from op amps. Right? Your op amp basically had a voltage transfer characteristic that looked just like this. Remember that? Except the op amp had an extremely steep slope, but it went from some high voltage to some low voltage when you passed a signal through its input that's going from low to high. And so this, you could even make an inverter out of an op amp. If you wanted to, you would. But in digital electronics, area is everything. You don't want to use the area it takes to make an op amp, which you've seen now. It takes many transistors for that, to do something as simple as an inverter function like this. And so the way that we make inverters is we use as few transistors as possible. And that's what we were looking at last time. So the last thing we were looking at is a one transistor inverter. Okay, so there's this transistor M sub S here, and I guess I have this in the actual lecture material too, so let's just go to this here. So we were looking at this transistor inverter with a resistive load. You can make it either with a bipolar transistor, but we criticize that, saying that it costs more because bipolar transistors are larger. Plus, there's power consumption that we don't want that is going on while we do this. So we don't do this necessarily. Let me make sure yes, I'm recording. And so instead of a bipolar transistor, and the early digital logic used bipolar transistors. This was in the 80s, this was happening. But after that, we quickly went to MOS, because MOS would consume less power and they're smaller. And the first MOS type circuits were like this. You had an MOS transistor and you had some kind of load. In this case, I have a resistor there. And so you can see what this is. This is exactly the same as a common source amplifier, right? You've seen this before in our analog domain. And so when you analyze this common source amplifier, what you see is some gain function from VI to V0. But that gain function, remember, was a negative gain. And so what that means is if I increase my input voltage, I'm going to decrease my output voltage. That's exactly what an inverter does. And so that's why this is a simple inverter here. Exact same circuit that we were using for analog to get gain, except instead of operating it at that point, I have this also in here. Instead of operating it at this point, this is where analog circuits are operated right here. We're operating it either here or here. And we want to spend as little time as possible in that analog range when we're in the digital domain. Because when you're in that analog range, usually that's where a lot of power is consumed. Okay, and we'll talk about that in just a bit. But we started looking at this circuit. And we started saying, okay, we want to determine what our output high and output low are. And so to do that, we take a look at the two different cases of inputs we can get in here. And in digital, those two cases are going to be a low voltage or a high voltage. And so if we make V in less than V input low, so say we put 0 volts into the gate of this MOS NMOS transistor, then this M sub S, I'm calling it M sub S, S for switch, the switch is off. And so if that switch is off, I've got nothing here going to ground. That means all of the current, the charge from VDD, comes through this resistor and charges up this capacitor. And it won't stop until it charges it up to VDD. Okay, once it hits VDD, it stops. Okay, then, whoops. In the output low state, what we're going to do is we're going to put an input voltage that represents a high voltage. So it's a large voltage. We're going to turn on this transistor in a big way here. And so in steady state, for M sub S, it's VGS minus VT, right? It's VGS is basically going to be VDD minus the VT. That's going to be a big voltage, right? And so when I put a big voltage here, what's supposed to happen is my output will go to some low voltage. That means I got a voltage big enough at the gate to keep the transistor on, but the output is such a small voltage that this VDD minus VTN is going to be greater than that voltage. That means the VGS minus VT is greater than the VDS, which means this transistor is in the linear region. Okay? So, when I have my output in a low state, this transistor is in the linear region, and basically the voltage that I have at the output is going to be equal to VDD minus the voltage drop across R, which is basically I sub D, whatever the current is flowing through this transistor times that R. And so I can write an expression for I sub D because I know the linear expression for I sub D, and this is it right here, with VDD as the input and with VOL as the VDS, which I'm showing there. In the last lecture, I think I'd written VDD right here. That was wrong. This should be VDL right here. VOL, sorry, for output low. And then I can rearrange this, right, and write out this equation here and try to get an expression for the output low voltage, and I would end up with something like this, and this ends up being a quadratic equation. I have a VOL here, I have a VOL squared there, I got another VOL there, and so this is something that I would have to solve a quadratic for to get that output low. And so this is the problem with biasing. This is basically a biasing problem that we've seen before in the analog domain, and with biasing, like we said before, you have to solve nonlinear equations. And for here, you would have to do that. Okay? Painful. However, like we did for analog, we can simplify things for digital to make it less painful. And so we can either solve this quadratic, or we can get a less accurate but still good value doing something else. So get a less accurate but still good value. Okay, how? By defining an on resistance for the switching device. Okay, and so what does that mean? That means I want to represent my circuit now by not just this. I want to represent the MOS transistor by just a resistor. Okay, so I'm going to have VDD here. It's going to go through that resistor R that I have in the circuit. This will be my output right here. There's my V0. But then from here, I'm basically, when I turn on the transistor, switching into what I'll call an on resistance associated with that transistor. So I have an R on there at the bottom there, and I'm going to have some input voltage V sub I that then controls whether that switch is on or off. Okay, so in this case that I'm looking at, I have a high V sub I. It's closed that switch. So in effect, what I have is a voltage divider circuit there. Okay? And so all I really need to know now, once I switch this in, is what is the value of this resistor R on, right? Because if I know the value of that resistor R on, then VOL is going to be equal to VDD times the voltage divider function, R on over R plus R on. Okay? I can write that differently. I can write that as VDD times 1 over 1 plus R over R on as well. So that tells me that if I want this to be very small, which is what I want, right? This is a V output low. I want that to be small. Then I want this R on to be as small as possible here, so that gets very large. I get a huge number in the denominator, and this becomes very small multiplying VDD. Okay, so the question is, what is R on? And R on then, the best thing to use is just use the current that's running through that transistor. Okay, so define R on as whatever the VDS is for that transistor divided by whatever its current is, ID. And so in that case, the VDS is going to be the voltage dropped across MS. That's going to be VOL, right? And so I'm dropping VOL across this. And so the VDS here is effectively VOL. Okay, and that I'm going to divide by the current going through the transistor. I know what the current is going through the transistor because we've already established that the transistor is in the linear region. So I'm going to say that the current is mu n times Cox times all of this here, W over L sub S, times what I have across the transistor here, basically all of this stuff here, VDD minus VTNS minus VOL over 2, that whole thing times VOL. And so in this, I'm going to get some cancellations here. So this VOL at the top cancels with that VOL here. It was a much bigger thing than I wanted. Okay, and so in the end, I could say that R on is just going to be equal to 1 over mu n Cox W over L S times this thing, VDD minus VTNS minus VOL divided by 2. Okay, and so these two together present a more simplified vision of what exactly this transistor is doing here. And so just to be perfectly clear, let me go red here. Let me put an arrow out this way to a star. Oops. Here I'll put a star here. Okay, we're really looking at this happening when V out is equal to VOL. I end up with this, with the switch closed. And my R on voltage there. Okay, so this is what I ended up with when I had my V output low. And this is a problem. Okay, this is a problem for me right now because I have current flowing. Right, I have this VDD across two resistors. Yeah, it's dragging this VOL, this V out equal to VOL. It's pushing that to a small voltage, which is what I need it to do. Right, I have a high voltage at the input. I have a small voltage at the output, but I have current flowing. And so if I have current flowing, that means I'm consuming power. So that current is going to be VDD divided by R plus R on. Okay? And so in digital, any current is too much. So I don't like that current. Okay, so let's define why any current is too much. So let's take a look at this I. And let's say that I was equal to 1 microampere of current. Okay, if I was equal to 1 microampere of current, then if I consider 100 transistors, that's okay. So for 100 transistors, that's okay. Because if I have 100 transistors, that equals 100 microamperes, right? Which is not that much current. Okay, but how many transistors do you have in your CPUs now? With cache and all of that, if you have 1 billion transistors now, right? Multiply that by this 1 microampere. Suddenly you have 1,000 amperes. Okay? That's way too much. How much power does your computer use? When you plug it in, how much power is it using? Yeah, it depends on your computer. Hundreds is still too high right now, right? It's probably in the 40, 30 or something range or something like that. Your phones are consuming even less. And so power is big, right? Your phones, what's the worst thing about your phones? You have to charge them, right? If you want to use them. And so here, we need much lower power consumption. And the solution to that is CMOS. Okay? That's different from what I just talked about. Here I talked about an MOS with a resistor logic. Okay? That is consuming too much power for me. On top of that, I could even complain about that resistor. Right? Remember what I said about resistors? They're too big too. They take up too much area. So the solution to all of this, and what they did before they had CMOS, which is a complementary device, they put a transistor in place of that resistor and they made it work like a resistor. And right, we talked about transistor derived, or resistors derived from transistors in your lab number 3, I think it was, right? You did something like that. And so they did that for a while, but when you do that, you still get that power consumption. And so the way to eliminate that power consumption is to use a complementary device, and that's where CMOS comes in, right? C stands for complementary in the word CMOS. And so we should talk about the CMOS inverter. And basically all this is about is us introducing a complementary device to ideally eliminate static power. Okay, so how does this look now? This looks like the following. If I have VDD here, I'm going to go into a PMOS device and stack that on top of an NMOS device, which it will go to ground. Both gates I will tie together to the same input. There's V sub I. And in order to avoid threshold change effects, normally what you do is you just tie your source for the PMOS and the NMOS to their bulks. Okay, that immediately eliminates all those complications due to threshold effects. I'll call this MP for my PMOS device. I'll call this MN for my NMOS device. And my output will be the same. Have an output voltage, and basically the next stage is going to be capacitive. So everything in an MOS circuit is based on capacitors. You're just charging capacitors. That's great because that means you're not losing any energy through a resistor to the other supply. Okay? And so let me just point out that we did this thing here. We tied this and this the way they are to eliminate body effect. Okay, and so with this we want to do the same thing that we just did with that inverter with the resistively loaded MOS inverter. Okay, we want to get first what the output high is going to be and what the output low is going to be. How do we define the ones and zeros here? And so I could start with the first case where the V input is less than my V input low. Okay, and you remember what these things are. Let me put this up so you see that, right? So V input low is right here. Okay, if I have an input less than V input low, then my output should be high. Okay, but first and foremost, if V in is less than input low, that means the transistor that'll be on is going to be MP, the PMOS transistor. MP will be on. Okay, the NMOS transistor, MN, will be off. Okay? And so if we have this situation, then we kind of have this. We have VDD, and if I represent my transistor again by a resistor, okay, so I'm going to call this RP on. Okay, and it's sort of a resistor in series with a switch. Okay, so that's RP on there. This is going to be my output here. With a load capacitor. Okay, so that's the PMOS transistor above. And let me actually do it the way this is, because the PMOS transistor is on, which means that the switch is closed. Right? That switch is closed. It's shorting that out. But the NMOS transistor is not on. So it has its on resistance here, but it's open circuited to the on resistance. So R sub N on is here. Right? And this then becomes my circuit. And so in this circuit, current cannot flow through that NMOS transistor down here. Right? Ideally, there'll be no current flowing this way. All the current will come down from here, and we'll have to make a turn here into C sub L. Okay, and so as it goes to C sub L, that means this thing, which represents the PMOS transistor, the PMOS charges this node all the way up to this voltage VDD. Okay, it's basically putting positive charge on this side of the capacitor. Naturally, the ground part will be the negative charge on that capacitor because you have to have equal and opposite charges there. But I could say basically that the output high voltage is just going to be VDD in steady state. Okay? And so that's my output high voltage for my CMOS inverter. And so now let's take the other case here to get the output low voltage. Let's do that on the next page. Oops. So let's take the case where my input voltage is greater than my V input high, okay, which means that I'm going to drive my output low. And so in that case, first of all, if I have that input, transistor MP, because that's a high voltage, it's very close to VDD, I have barely any voltage from VDD to that input, which means the PMOS transistor is going to be off, right? So MP is going to be off. MN is going to have a lot of voltage across it, so it's going to be on. And so now my circuit looks like this. I have my VDD. That's my RP on. This is going to be an open circuit. But then RN on is going to be shorted to my output, which is going to a load capacitor. And in this case, if I had some positive charge here, okay, what it's going to do, let me do that in another color. If I had some positive, too thick, right, this positive charge Q here has no choice but to discharge to that RN on down to ground there, right? And so basically I have this current here, and the NMOS discharges capacitor C sub L to 0 volts. Okay? And so in the end, the V output low for a CMOS inverter is 0 volts in steady state. Okay? So we've now established the output high and output low for a CMOS inverter, and what we find is perfect. It's ideal. Right? We want it to be the output high to be VDD. We want the output low to be 0 because that's well within the noise margins for the next stage. Right? This output has to drive another digital stage that's going to be based on MOS, and so it needs to be as low as possible if it needs to be low, as high as possible if it needs to be high, and it is. Okay, so that's what's great about CMOS right there. And so the next thing that we want to do, and I guess we're out of time now, but the next thing we want to do is determine the voltage transfer characteristic for this device. And so let me at least just start this here. We want to determination of the voltage transfer characteristic. Or VTC, something you've measured before in lab, but for op amps. And so we want to determine that thing that I've been pointing at this whole time. We want to determine this. And so we'll make an attempt to grab this. That attempt didn't work. Try another one. There we go. There it is. And okay, so there's our voltage transfer characteristic. And so what do we know so far about our CMOS and yikes, I don't want to do that. So what do we know so far about our CMOS inverter? Well, we've now established that the VOH is simply VDD. Okay, and the VOL is ground, which is 0 volts. Okay. The other things that I want to know about this is I want to know what VIL is and what VIH is. Right. I know that VOL here already, output low, saying the same thing. That's 0 volts. That's VDD. Okay. But I now need to know what VIL is and VIH is in order to determine this noise margin. And so the reason why I care about that noise margin is because, say my voltage was at 0 volts, but say some switching event happened nearby, I can get a spike of voltage here that, if large enough, can actually switch this thing to the other side. And if this were feeding a flip-flop, that flip-flop would be permanently switched to the wrong bit. Okay? And so this is what we're going to do next time, but we're out of time right now, so I'll see you on Wednesday.